Hi everyone, I'm Lily Liu from UC Berkeley. Today I'm going to talk about our project, Leveraging Application Data Constraints to Optimize Database-Backed Web Application. This is joint work from UC Berkeley and UChicago. As database researchers, we know that data constraints are useful because it defines the semantics of the data. And one of the most important applications is query optimization. Let me give you a concrete example. Suppose we have two tables. The first is the users table, which defines the user information. The other is the members table, which defines the membership information. For example, a user can participate in one or multiple projects, and a project can also have one or more multiple participants. So there are different data constraints here. The first type of constraints is foreign key constraints. For example, the user ID column of the members table must reference the ID column in the users table. Similarly, the project ID column in the members table must reference the ID column in the projects table. There are also some uniqueness constraints. For example, the ID column is a primary key, so it's unique. Moreover, the user ID project ID column pair is also unique. For example, here row 1 and row 3, both the user ID and project equals 1. So actually this record is invalid because we require that the user ID project ID pair is unique. But with those data constraints, what can we do? It can rewrite queries. So what it means is, for example, if you want to find the information of distinct users who participate in the given project, you will have some SQL query like this. But actually, it turns out that given the uniqueness constraint, the distinct keyword can be removed safely, because once you fix the project ID, the unique ID will also be unique. And you use them to look into the users table, the output will also be unique. So you don't actually use a distinct keyword anymore, it's unique itself. And it turns out that by removing this distinct keyword, you can actually accelerate the query by 1.65x on 100K records. So this tells us that data constraints are important. They can be used to simplify or rewrite queries. But the problem is that in database-backed web applications, those data constraints are always hidden. For example, when the user clicks the button on the website, it will trigger some endpoint on the application code. The application code will perform some calculation, do some data validation, and then it will send the SQL query into the database so that the user information, the modification, will persist in the database. The traditional method try to find those data constraints by looking at the database itself. They will use some statistical or machine learning method on existing data to extract those constraints. And this method has some problems because, for example, data is not always available. It's hard to get the data. And the second is, those statistical or machine learning method cannot guarantee that the constraints extracted are always valid. It's possible that those constraints might be invalidated by future data. So those constraints are actually not very easy to get. Another thing we observe is that those constraints are actually in the application source code because those data are generated or validated by the application logic. Instead of extracting those constraints from the database, you should look at the application source code and extract the constraints there. So there is a gap between the application code and the database. Database is unaware of the constraints which are defined in the application code. So that is what COCO tries to do. COCO tries to analyze the application source code and extract those constraints defined in the application logic and send them into the database for future optimization. However, we find that query optimization with data constraints is also difficult. Like even if COCO can extract those constraints and send to the database cannot optimize them. What does it mean? Like still the example here, say if you have a SQL query and you have some data constraints extracted by COCO, and you want to optimize a SQL query based on the given constraint. And we look at existing open source or commercial database, and we find that none of them can support all types of query rewrites we find in the literature. The main reason is that they are using a heuristic-based method to extract those constraints, and the heuristic cannot cover all the cases. So the second contribution of Coco is that we develop an automatic way to leverage those constraints to optimize queries. And it is automatic, it's not heuristic-based, and it can support different types of query rewrites automatically. So in this talk, I will give you an overview of Coco, and I will talk about how we extract constraints and how we use extracted constraints to perform different optimizations, followed by the evaluation. And in the evaluation, we will try to answer the questions like how many constraints are hidden, how many queries can be optimized, and how much performance gain Coco can get. So the system of Coco consists of two components. So the first one is the offline optimization, which outputs a lookup table that has the original query and optimized query pair. This is an example, right? Like the before is the original query, and the after is a query with a distinct keyword removed. And during the online query processing, it will send the query to the Coco system, and Coco will check if the query already in the lookup table. If it's in the lookup table, it will send the optimized query to the database instead of the original query. Another thing to mention here is that Coco rewrites the query based on query template. So here, instead of putting in the concrete value, we will use a $sign as a placeholder. So in the future, as long as the queries has the same satisfy this template, they can be optimized. They don't have to have the exact parameters. And for the offline optimization, Coco performs them in 3 steps. The first, it will extract those constraints from the application source code. Next, Coco will extract queries from the application test log. And lastly, based on the constraints, Coco will do 3 types of optimization. First is optimize the data layout. Second is adding the pre-checks to avoid the unnecessary communication between the application and the database. And lastly, Coco will rewrite the queries based on the extracted constraints. So to perform the constraint extraction, we need to first understand how a database-backed application works. Still the example before, like when the user tries to participate in a new project, it will trigger some endpoint in the application code. Here, like the application code will create a new member record, which records the membership information. And it will also trigger the line which saves the record into the database. And what is a member class? Right here, we create a new member record. So in the member class, it will define some, data constraints. For example, given the project ID, the user ID is unique. And when the line of member.save is actually triggered, it will first, the framework will translate it into a SQL query to check if the record already exists in the database. If it's in the database, it will throw an error because the record already exists. Otherwise, it will insert the data into the database by issuing an insert query. So as can be seen from the example here, the validate API defines the semantics, the constraints, the data must to be satisfied. Otherwise, the framework will errors. So we Coco extract the constraints by pattern matching on the data validation APIs, and we can support unique inclusion format, length, numerical presence, and customized constraints. With the constraints extracted, Coco first perform two types of optimization. First is add pre-checks. Second is optimize data layout. So for adding the pre-checks, let's look at by example. The code here tries to find the user with a given username, and the username is in the parameter, which is a user input. So what will happen is that the framework will translate into a select query, try to find the username that equals to the user input username. But if we know that the username must satisfy some format constraints, satisfy this regular expression, instead of triggering this line directly, we can actually modify the application code by adding some pre-check. So we only send the SQL query to the database when the input parameter satisfies this regular expression. So if it does not satisfy this regular expression, we will do an early return. So it can avoid those unnecessary communication between the database and the application. The second type of optimization we do is optimizing data layout. Like for example, if we know that the status column can only take the value of pending, active, fail, unknown, we kind of know that this column can only have 4 possible values. And instead of storing in a string or varchar, we can translate into the enum data type so that it can reduce the storage and maybe improve the performance a little bit. And the last type of optimization we do is query rewrite. So given the extracted constraint and original SQL, Coco will use some heuristic to enumerate all the potential rewrites and sort them by the cost. The cost is estimated by the optimizer. One thing I want to emphasize here is that the enumeration does not guarantee the correctness. It's possible that those queries rewrites are not equivalent to the original SQL. So that's why we need the following steps. So in the following steps, we'll first test those rewrites on a small sample database to filter out those obviously wrong rewrites. And next that, we'll use a verifier to verify that the rewrites and the original query are equivalent based on the given constraints. The reason we need the sample database because that verifier is kind of expensive. So we want to reduce the number of queries we want to verify so that it can reduce the overall optimization time. So we will do this for each query, and we will return the first rewrite that is equivalent to the original SQL, but also has the lowest cost. To evaluate Coco, we evaluate on 14 real-world applications covering different categories, and we evaluate on AWS with Postgres as a database. And we also synthesize the data set so that the data size is about 5 to 10 gigabytes for each application with 10K to 1 million records per table. So first, we find that Coco can extract around about 289 constraints for each application. And there, more interesting, we find that there is only 12% constraint overlap between database and application. So database means that the constraint is already defined in the database without looking at the application code. But the 12% here indicates that the overlap is not big. So there are a lot of constraints actually only defined in the application source code. Next, we try to understand why is the case, like why the application and database have different types of constraints. So we look at the type of constraints, and we find that for inclusion, format, and numerical constraints, they are only defined in the application code. We guess that it's because that defining them in the database requires writing UDFs or as check constraints, which is not very straightforward. So the developers might prefer to implement them, like write them in the application code, which is in Ruby, and it might be much easier than define them in the database. So with the given extracted constraints, we use them to do the optimization. The first one is change the data layout. And we find that it can reduce the storage for those columns by about 2.19x. And it can also improve the performance a little bit. And by adding the pre-check, because we don't have the real world user input, so we simulate it. When 80% of the input is invalid, we can have an average speed up of 5x. And adding the pre-check introduces negligible overhead. And for the automatic query rewrite, we plot the number of rewrites after each step. And we find that removing those slow rewrites, adding tests, those steps, they can filter away a considerable amount of incorrect or slow rewrites. And eventually, 1,894 queries are sent to the verifier, and an average of 415 queries can be optimized. With regard to the performance, about 2% to 20% of queries can have a speed up of more than 2x. So we also look into we also try to see if the database can leverage those constraints. So what we do is we don't perform any rewrite, we only install those constraints into the database. And we find that the speed up is not very impressive. So what we do is next, we rewrite those queries, but we don't install the constraints. And we find that more queries can have higher speed up. And lastly, we install both constraints and perform query rewrites. And we find that we achieve the best performance. So some queries, they can benefit by both installing constraints and rewriting the queries. One last thing is that we find that there are some slowdowns on the picture. This is because the optimizer fails to predict the cost correctly. So in conclusion, the data is increasingly being created and maintained programmatically. Using ML to extract those constraints is just an overkill. We can just analyze the code and extract the constraints. And COCO is the first tool that identifies the constraints by analyzing the code, and it leverages the constraints to optimize application performance. And it also employs an enumerate test verify technique to automatically rewrite queries. So I encourage you to check out our paper or code if you are interested. Thanks a lot.